Okay. All right. Time to do bit manipulation. Count bits. Given an integer n, count the number of ones in the binary representation of every number in the range 1 to n. Return an output where output I is the number of ones in the binary representation of I. So this is like simple enough. As you know, the trick of manipulating bits. So it's a matter of so for I in range of n, we will have 0, 1, 2, 3, 4. So we're gonna increase n plus 1, have a resulting list that we're gonna append with num. The num is first gonna get initialized to 0. And then we gotta think while I is less than n. So when I is not equal to 0, we're gonna shift by 1. Problem is, gotta remember the exact ways we do this. Else we're gonna have num appended and then we return result. So this is where we do bit shifting now. The bit shifting that occurs here. So from what I remember, this is something this is another thing. Now, I think it'd be better if I just have a quick look here. Right. Okay, so number of 1 bits. The problem is we also need to have my boilerplate code up, which will help me here. So you can detect if 1 is on the right end and shift the bits right by 1. You can read only 1 bits with the following. Okay. Yeah. Okay. You can only read the 1 bits from doing the following. Okay. So one and n minus 1. Gotta double check. N and n minus 1. Right, that would make more sense. I and I minus 1. This can be simplified to I and wait. No, okay. and, okay. Gotta remember where that and symbol is. Equal I minus 1. Okay. Num plus equals 1. 1, 2, 3. So the other way would have been to do this if 1 and I. Right, 1 and I is equal to 1. I think that was the check. Then num plus equals to 1. And I is equal to I bit shift right by 1. Okay. Is that right? Okay. However, this is better or simpler to remember. GG. Why are there so many different ways to solve this problem? Hello, Alexander Petronov. Happy New Year to you too. It has been a long time no see, that is correct. I haven't seen you there in a while. How could this be optimized even further? We'll have to watch.
Hey everyone, welcome back, and let's write some more Leetcode today. So today we're going to be solving a binary question, counting bits. And this is one of the binary questions from the blind 75 list that we've been tracking in this spreadsheet. So we will finally be adding a video solution to this binary problem. I'm pretty sure it used to be a medium problem, which is why it's highlighted yellow, but I think it got changed to an easy problem. So the statement is pretty simple. We're given an integer n, and we want to return an answer array of length n plus 1, basically a value for every integer in the range from 0 all the way up until n. So if n happened to be 0, then we would just return a single integer. If 0 happened to be 2, then we would return 3 integers for 0, 1, and 2. And basically, for every value in this range, 0 to n, So if n was 2, we would have 3 values in that range, 0, 1, 2. For each of these values, we want to know what is the number of 1s in the binary representation of this particular integer. Now, what's the binary representation of 0? It's, of course, just 0, right? You could add...
How do you do a bit manipulation DP? That DP looks kind of sus.
multiple zeros, but it's still going to be 0. What's the binary representation of 1? It's going to be just 1, right? You could have some...
The stream is lagging a bit. Yeah, that might be the case. It might be because of the upload speed that I have. And this might be better or worse. Sorry, I did disconnect VPN in the middle of the stream. But this should be better, I think, now.
leading zeros, we could have as many as we want, but at the end it's just going to end with a single 1, so there's only one occurrence of the integer 1 in the binary representation of 0. So far our output is going to look something like 0, 1, and then now we just need the number of 1s in the binary representation of 2. The binary representation of 2 is going to look like this, 1, 0. You could have some leading zeros, but this is the main part that we're looking at, so it just has a single 1, so then the output is going to be 1 for that. So the array that we would return is going to look something like this, 0, 1, 1. Now the brute force way to solve this problem is going to be n log n, and that solution is going to look something like this. Let's say we had an arbitrary value such as 2 or maybe even 3, right? We know the binary representation of 3 is going to look like 1, 1. Right? So how are we going to count the number of 1s in the binary representation of 3? Well, first let's get the 1s place, right? Is this going to be a 1 or a 0? How can we get that? Well, we can take 3, mod it by 2, which is going to give us 1. So we have at least 1 1 here, right? So we already looked at this position. So what we do is basically cross it out, and then we just want to look at the remaining portions. Now, how can we actually do this? Like what kind of operation can we do? Basically, if you take 3 and divide it by 2, integer division here, and most programming languages will do this basically by integer division. What that's going to do to this integer is it's basically going to take that 1's place and remove it, take the remaining bits, and then shift it to the right. So it basically does exactly what you would want to do. And of course, what do we get when we take 3 and divide it by 2? Integer division is going to give us a 1, so we're basically going to get this, and when you look at that, yes, this is the binary representation of 1, right? So now we're going to take this and mod it by 2 as well. We're taking 1, modding it by 2. That's also going to be a 1. So far we've counted 2 different 1s for this integer, and again, we're going to take this 1's place now and chop it off, and now we're left with a single 0. So if you take 1 divided by 2, yes, you get 0. Once we get to 0, that's how you know when we're stopping, right? There's obviously in 0, there's no more 1s in 0. So basically we counted 2 different 1s. So that's how we would do it for every particular integer. The example I showed right now is 3, and to get this, the time complexity is log n, because for any integer n, how many times can you divide it by 2? Well, of course, that's just log base 2n. Now, we don't really worry too much about the base usually, but yes, it's going to be log n, log base 2n. That's how many times we could divide any particular integer n by 2. And of course, we know we're doing this for a bunch of integers in the range all the way from 0 to n. So we're doing this n times. Doing a log n operation n times is going to be time complexity n log n. Now there's some repeated work that we can eliminate that you can easily recognize when you actually draw out the bit mappings, the binary representations of a bunch of integers, and with that repeated work we can actually get a working O of n solution. Let me show you that right now. Now I just drew out the binary representations from 0 all the way up to 8. So we know that of course 0 drew out the binary
Hold on.
times is going to be time complexity n log n. Now there's some repeated work that we can eliminate that you can easily recognize when you actually draw out the bit mappings, the binary representations of a bunch of integers, and with that repeated work, we can actually get a working O of n solution. Let me show you that right now. Now I just drew out the binary representations from 0 all the way up to 8. So we know that of course 0 has 0 and 1s in the binary representation. When you get to 1, we have 1 occurrence of 1 in its binary representation. For 2, we have 1. For 3, by looking at this, we can see we have 2 different ones. And now when you get to 4, you really start to notice how we are doing this repeated.
Hello, Matran. How long have you been grinding Leetcode? Like throughout this year, or throughout last year, I would say. Yeah, here's my Leetcode history. I'll bring it up. It's my history. So you can see like periods of stopping and starting. I kind of went hard for a bit, and then I kind of went more consistent for a bit. Did AWS interview rounds have a lot of Leetcode questions? The interview rounds, they had basically a question per interview, and I had 3 interviews. That's basically the scenario. So just got to be prepared. And for me, those questions were related to, it was an array problem, it was a graph problem, and it was another array problem, I believe. So nothing too hard overall once you get Leetcode down. But again, like, it's not even about solving the problem, it's about speaking it through.
Work. Notice how for 4 all the way to 7, we have a 1 in this place, right? In the most significant place, we have a 1. And notice how the remaining portion of this, and then...
Did you ask the interviewer for hints during? Yes, I would, but I didn't that time. I didn't need to, but if I was going down the wrong approach, if I spoke well enough also, the interviewer does nudge you in the right direction. So I didn't ask explicitly for hints, but they told me to go down a specific route of thinking sometimes. Or, you know, ask me questions that would get me to think down the specific route that we needed. Yeah, so it's, you know, not too bad always during the interviews.
This, and then this, and this, these 4 are just repeats of the previous 4 that we calculated, right? Because we're counting 0, 0, adding a 1, right, to 4. When you add a 1, you just change it to this. From 4, when we add a 2, we get this, which is basically the binary representation of 2 itself, right? And then you get a 1, 0, and then you get a 1, 1, which is matching over here. So now looking at it, this is the binary representation of 4, right? There's just a single 1 in this position. So if we wanted to take 0 and add 4 to it, we would just take this position and add a 1 here, right? That will take us 4 positions ahead. And if you had a 1 and you change this bit to a 1, we're adding 4 to it. So you can take a 1 and change it to a 5 by taking that bit.
Yes.
So similarly, when we get to 4, we know that, yes, we're going to have 1 extra 1 in this position, right? Because we just
Can't believe this is a bit manipulation and dynamic programming solution.
This is the most significant bit so far. But for the remaining ones, all we have to do is take this, offset it by 4, and get here and count how many 1s were over here. So when we're calculating how many 1s for 4, we're just saying it's 1 plus the number of bits at position 0. How many bits how many ones were in position 0. That's our DP. So you can see this is a dynamic programming problem because we're using the previous results that we calculated to compute the new results. In other words, this is going to be 1 plus DP of n minus 4.
N minus 4
when
for
you
sure,
look at
that's
this
true.
5, we're also offsetting it by 4 to get
That's
these
very true.
2, right? Because that's what's going to match up with this, which is going to tell us how many ones are going to go here, right? So and clearly we see that that's a 1. So here we're going to compute 1.
This is a good question. Whoops.
Hey everyone, by looking at the 1, this is the, in this case you can do 4 to get these 2, right? Because that's what's going to match up with this, which is going to tell us how many ones are going to go here, right? So and clearly we see that that's a 1. So here we're going to compute 1 plus, again, dp of n minus 4. And similarly for here, we would say 1, which is coming from here, plus the number of ones in this binary representation, which we know we already computed up over here, and the answer to that was 1. So in this position, really there's going to be 2 ones in this binary representation. Now over here, once again, we know that there's at least 1 from here, plus how many were in this binary representation. We computed that at position 3, which again is offset by 4. So this is going to be 1 plus 2, which is going to be 3. Now you get over here. So now we have an even more significant bit. Last time the most significant bit was in this position, and we know that represents the integer 4. Now we got an even more significant bit, which represents the integer 8. So we know that this is going to have at least one occurrence of 1, and then we want to know how many ones are in this binary representation. Now, how are we going to get that? In this case, you can tell the offset is no longer 4, because if we do an offset of 4, we get to the integer 4. That's not what we're trying to do. This binary representation represents the integer 0. So in reality, we want to take 8, offset it by 8, which is going to get us all the way over here. And once you do that, that's when you actually notice the pattern. Since this is going to be 1 plus dp of n minus 8, you can tell that for each value, this is going to be the equation 1 plus dp of n minus a particular integer, and that integer is going to be called the offset. And the offset is going to be the most significant bit that we have reached so far. And what are the most significant bits? Well, the first one is going to be a 1, the next one is going to be a 2, the next is going to be a 4, 8, 16. So basically they're doubling in size every time, because we know a bit is just a power of 2, right? That's what binary represents. So let's clean this up just a tiny bit. So we know that this is kind of our base case. 0 is going to have 0 ones in it. Now, in the next position, what's the most significant bit we've reached so far? It's in the ones place, right? So therefore, it's going to be a 1. So when we're computing this, we're going to compute 1 plus dp of n. N is always going to be the value we're computing right now, so that's going to be a 1 minus 1, because 1 is the most significant bit we've reached so far. Down here, we reached a new significant bit of 2. Right? Because we've gotten to the value 2 so far. So for here, we're going to say 1 plus dp of n minus 2. Now in this next position, again, the most significant bit is 2, right? We know that 2 is a significant bit. The next significant bit is going to be 4, because that's another power of 2. So 3
Very good explanation.
It's still going to use the previous value. So from here, we're going to compute 1 plus, again, dp of n minus 2. Now, once you get here, we see that we've reached a new power of 2. So then we're going to be modifying this to 1 plus dp of n minus 4. And then, of course, when we got to 8, we know we reached a new power of 2, so we were going to do 1 plus dp of n minus 8. How do you know if you reach a new power of 2? Well, you can take the previous power of 2. For example, it was 2, right? Let's say the current power of 2 is 2. And let's say we multiply it by 2. Does that equal the current value we're at? If we got to 3, n equals 3, we would check, does 2 times 2 equal 3? No, it does not. So we did not reach a new power of 2. If we got to 4, 2 times 4, that does equal 4. So now we reached a new power of 2.
Yep.
And then from 4, we would do the same thing. So 4 multiplied by 2, does that equal to 7, right? Let's say we got to 7 and we were trying to see, is this a power of 2? no, this does not equal 7. But once we get to 8, then 4 times 2, yes, that equals 8, right? So we did reach a new power of 2, and we'd do the exact same thing. So the next time we reach a new power of 2 would be 8 times 2 equals 16. So next time we reach a 16, that's going to be a new power of 2. And 16 times 2 is 32, etc., etc. So that's how it's going to work. And once you know this idea, it's not super intuitive until you actually kind of draw it out. But once you do, the code is actually pretty easy to write. Let me show you how. So our DP array is going to be initialized to all zeros.
Is there a max size to the DP array? The max size to the DP array is the size of n, right? So technically, isn't it O of n space? It would be O of n space, no? How is space complexity of O of 1 and a time complexity is O of n? I would assume that space complexity is O of n here. So very interesting how that's the case. Let's watch this coding explanation.
And it's going to be length n plus 1 because that's how many we're trying to compute. And we're also going to have an answer array, which is initially just going to have a single 0 in it because we know n is going to be at least 0. And then we're going to go through for I in range all the way from 1 up until n. So n plus 1, this is non-inclusive in Python, so we're actually going to be stopping when we go from 1 all the way up until n. And we're going to be keeping track of one more variable, the offset, aka the highest power of 2 so far. So initially that's going to be 1. So before we actually compute the DP or the number of bits in this integer i's binary representation, first we're going to check can we double our offset. We're going to check if offset multiplied by 2 is equal to I, the current n that we have just reached. If it is, then we can set offset equal to I, otherwise offset is going to stay the same, and then we can actually compute the DP. So we're trying to compute DP of I, which is basically the number of bits, the number of ones in I's binary representation. We know that's going to be at least 1 plus DP of I minus the offset. And actually, one thing I just realized is the DP.
Hold on, right? So if offset times 2 is equal to I, then you would make the offset the new I.
DP and the answer array are actually the exact same. I don't know why I even created an answer array. We can get rid of that. So this DP is basically our answer array. It's going to give us the number of bits, the number of 1 bits in each integer's binary representation.
So that's why.
Once we're done with that, we can go ahead and just return this DP array. So as you can see, this is a pretty efficient solution.
So you're telling me that because you returned the DP array, it is O of 1. That is a smart way to do it, I suppose, you know what I mean? Alright, so let's write that out. Trying to just go based off memory now. So this is 0 for everything up until n plus 1. For I in range of n. Now we want to go from 1 to n plus 1. We're going to say that we got to keep an offset, which is going to start from 0 to begin with. And then if offset is equal to offset, I should say offset times 2. If I equals offset times 2, offset gets left shifted, right? left shifted 1. If you start from 0, you left shift 0, is that not just still 0? So you need to make 0 equal to the highest significant bit of... So you need to make this 1. Then you can shift it. Yes. And then you say dp of I is equal to dp of I minus the offset, which is the number 1 plus. Why 1 plus? 1 plus because we're one more significant bit higher up. Let me see this. Because when we get 0, 4 gets 1 significant bit higher, 5 gets 1 significant bit higher, 6 gets 1 significant bit higher, 7 gets 1 significant bit higher, 8 gets 1 significant bit higher than 1, 9 should get another significant bit higher than 1. Yeah, okay, that's still crazy to think about. And then return dp. That's a crazy solution, I would say. That's a pretty sick solution. Guy you can trust. To be honest, I've done over 1k problems across different platforms and I've never been given the chance to interview, even for help desk roles. Really? Where, if I may ask, which country are you from? In the dynamic programming approach, so this is still bit manipulation. The bit manipulation, number of 1 bits, I should also say. Bit manipulation should also make a bit manipulation tag here. USA. I feel like I'll never work in software, but I still do it for fun. Nah, here's the thing, man. Eventually you will. Right? I believe you will. If you've done so many questions, I'm convinced you're even smarter than me. Like, for the problems that you've done so far, or more experienced than me, I should say, you know, I feel like you are happier to do this type of work, and eventually you'll get something, you know, just keep at it. It's unfortunate for sure. I will say, like, I feel incredibly lucky for getting what I got. But I'm sure you can do it too, you know. Just give it time. Just give it time. In the dynamic programming approach, The largest or smallest significant bit? Like, what is a significant bit, by the way? Okay. There is one photo or one clip or one screenshot I
Hey
can take
everyone,
that will make this so clear to me. Okay, so I know this is the accepted solution, but we will put a better solution. It's a very good solution. Very good problem, I would say.
zero. So in reality, we want to take 8, offset it.
I just need to take one screenshot of this. And then the rest I will understand when I get back to this. When I get back to looking at this. Okay. That's alright. That's alright. This is good. This is such a good problem, I will say. Alright. That's probably enough time for this problem now. Reverse bits. That's going to be an interesting problem. I want to solve this later, though. I don't want to solve this now. Okay, I'm just going to call it, guys. Thanks for being here. I will be hopefully back. I should still try and do more, right? I still want to do more. And yeah, we will try and do more. So we'll keep it up coming into the new year. Alright. See you guys. Peace.